Hello, my name is Igor and welcome to another My Tech Fun episode where I have the filament testing, and this time from the eSUN, the ABS Plus versus eASA. Now, a month ago approximately I had a comparison video where I tested eSUN ABS Plus versus polycarbonate versus nylon, and there I used this ABS Plus in white color, and I got several comments that white color for some reason has a weaker layer adhesion because of some additives. Okay, so for this experiment I bought ABS Plus in black color, so I bought it myself, but the eASA, this was sent to me by the eSUN. And I will repeat those regular mechanical tests which I usually do on this channel, so the results are comparable with those from earlier videos. And also I include here the creep test too, because I want to see is there any difference between ABS Plus or ASA if I want to use them for 3D printed parts for, let's say, Voron or similar printers, which will print on higher temperature. Let's say inside the enclosure it will be 40-45 degrees Celsius. This is from eSUN mechanical specification table. If I compare the ABS Plus and ASA, I can see that they are very similar materials, but except on few points. For example, the ASA had a heat desertion temperature of only 54 degrees Celsius, which is very strange, until the ABS and ABS Plus 78 and 73 degrees Celsius. Another very big difference is on isolated impact strength. The ABS Plus has approximately twice as bigger strength. And actually this may be true because on my isolated impact test, this was first time that the test specimens didn't broke under a half kilogram hammer. But of course we will see, because I will compare now these two materials. They have the same color, same manufacturer. Now theoretically the ASA is a little bit expensive. It is UV resistant, that's the biggest difference from the ABS Plus. And theoretically it should have a little bit less warping, so it should be easier for 3D printing, but we will see. I think in both cases I will use the enclosure and I will use some glue stick probably for better bed adhesion. The printing temperature is equal between 220 and 260 degrees Celsius in both cases, and also the recommended bed temperature is same, between 90 and 110 degrees Celsius. So I will start with printing a temperature tower, and then I will print those test specimens and start with the mechanical experiments. Of course you can always skip this part and jump straight to results, but there is an option, so if you want to see the full video you can do it. And now let's start with the unboxing and temperature tower printing. I'm starting with the ABS Plus in black color, and the first will be printing a temperature tower. And the spool is in nice vacuum packaging. We have some basic information on the spool, that the printing temperature is between 220 and 260 degrees Celsius, and the bed is between 90 and 110 degrees Celsius. What I'm missing here is some kind of scale here. Here we can see how many filaments we have on the spool, but it would be good to see some kind of scale in grams or in meters. And everything will be printed on ND3V2, where I have a direct drive extruder and all metal hot end, so I can print on even 260 degrees Celsius without a problem. And it will be inside the enclosure. I have this reality enclosure. And I will monitor here the temperature, and I'll try to keep approximately 45, max 50 degrees Celsius inside. And as you can see, I moved the screen outside. If you're not familiar with printing inside the enclosure, what is important that you don't need too big temperatures inside, but when you reach those 40-45 degrees Celsius, don't open it to prevent any kind of breeze or moving of the air. And now no opening until it's finished. Interesting, it doesn't curl up like the white color. And the temperature inside the enclosure is 46 degrees Celsius. And the printing is almost finished in a little bit less than 2 hours. Immediately I want to check the bed adhesion, which is great. I will wait until it's cooled down and then I will try to remove it. And if I analyze this temperature tower, the bridging is almost equal on any temperature, and there is no stringing. Usually that's not even the problem with ABS. But I see that there is a difference in overhang. And if I would analyze these temperature towers, probably I will choose the 240 degrees Celsius for the printing. But I want these results to be comparable with those from the previous videos. And there I print everything on 250 degrees Celsius. And if I compare that temperature tower with this black one, I cannot see any significant difference. Maybe the bridging is nicer on this one, but maybe that's only because of the color. Here I broke those candles earlier to check the layer adhesion. And the overhangs is also very similar, maybe a little bit better on the black filament. So all test specimens will be printed on 250 degrees Celsius, bed temperature 105 degrees Celsius, and I'm using a Wham Bam PEX with the glue stick, and cooling is 12%. And the printing is finished in approximately almost 5 hours, and the temperature inside the enclosure was 47 Celsius. And here all ABS parts are printed. I will mark them with this golden marker. That was the ABS. And now it's time to print ASA, and basically I will use the same G-codes as for the ABS. It has also nice vacuum packaging with some silica gel inside. And interesting, the spool is now transparent compared to the ABS spool. This is in black non-transparent color. And here we have this sticker with some basic information about the printing temperature. And again I'm using this PVA based glue stick for better bed adhesion. And I'm printing the same G-code. The bed adhesion is good so far, but I will close the enclosure completely. Currently it's printing the second element on 250 degrees Celsius. And printing is finished. Inside the enclosure it was 46 degrees Celsius. And the bed adhesion works very good with this PEX sheet and the glue stick. So I have to wait until the print surface cools down, and then I will compare it with ABS Plus. The ASA parts will be marked with silver marker, and the ABS Plus are with the gold version. Now let's compare the ASA and ABS Plus temperature towers. The bridging and the stringing is equal on temperatures on both filaments. Maybe I can see a little bit more difference in overhangs. So the overhang came out better on the ASA, and it's a little bit more shiny filament. And of course here I will print all test specimens on 250 degrees Celsius, so they will be comparable with each other. And I'm using the same G-code, and all test specimens will be printed on the 250 degrees Celsius. It's a good start, but I know that the bed adhesion is not the problem with this combination of the bed surface and the glue stick. The printing is almost finished, maybe 2 more minutes left, and the temperature inside the enclosure is 46 degrees Celsius approximately. Printed in almost 5 hours. And all ASA test specimens will be marked with this silver marker, and as I mentioned earlier, ABS are marked with the gold version. When it cools down, it's very easy to remove these objects, even if I use the glue stick. And I have all test specimens printed, and now it's time for mechanical tests. Starting with tensile test, this is ABS Plus, 4x4 mm, the smallest cross-section area. And this is now ASA. And this is how they broke, all on the smallest cross-section area. This makes me think that the layer adhesion is okay, but we will find out in the next experiment. Layer adhesion test. These test specimens are printed in vertical position. Smallest cross-section area is 4x4 mm. Starting with ABS Plus. And now ASA. Visually no significant difference. See, the numbers I can see only when I edit the footage, but for the feeling definitely the ASA was much stronger than the ABS Plus. And don't forget they were printed on same temperatures. And now let's check the shear stress. This is double-sided shear stress. The cross-section area is 5 mm. And now ASA. Where some parts are missing, but both objects was shared on those two cross-section areas correctly. And this is 3-point bending test. Distance between supports is 50 mm, and I'm starting with ABS, and I will record the load at 2 mm deformation and the maximal load. And this is the ASA test specimen. The ABS Plus didn't broke, just deformed, but the ASA, it broke. Not complete, but partly fraction. And this torque or twist test, I have these test specimens with diameter of 6 mm, the length is 22 mm, and this side goes into the vase, and the other side goes to this wrench torque meter, and I will record the torque at 90-degree rotation and the maximal torque. Starting with ABS. 0.8. 0.9 was the peak. 0.9 is the 90 degree. Oh, now it broke, 1.2. ABS ASA. Similar break, but the ASA broke on higher torque. And it's time for the isotope impact test, and here I'm expecting some biggest difference between these two materials. According to manufacturer specifications, the ABS Plus has at least twice as bigger strength compared to the ASA. And actually this was the only test specimen which didn't broke under half kilogram hammer. I have 1 kilogram hammer too, but I got some skeptic comments that I decided to use a half kilogram hammer. So I'm expecting that it will not break the ABS Plus test specimen, and I'm curious what will we do with ESA. ABS Plus. And it didn't broke completely, but almost. ASA. 0 position. ASA was quite strong too, but so let's analyze it digitally. This is the scale, and this is the 0 position of the hammer, and this is after breaking the ASA test specimen. And this is after breaking the ABS Plus test object, and don't forget, so this is not really measurable because it didn't broke. But approximately I can see it is very close, so yes, it is possible that it is twice as stronger than the ASA. And if I measure everything from the 0 position, I can use these values to calculate the breaking energy. And to get some numbers for the ABS Plus, I will place in a graph that it is really double the strength of the ASA. I want to measure the hardness of these materials. I will use short D durometer, And I'm not sure about the plastic, but from metals I know that from hardness we know approximately how is the wear resistant of that material. I'm starting with ABS and I'm measuring perpendicular to the layers. 71, 70, 72, 70, 70.5, 71. And looks like even the hardness is very similar for these two materials. It's time for temperature test. So this is the ABS Plus and this is ASA, and I hope that that information in the material properties table by the eSUN is wrong, because I would be very disappointed if ASA would start with deformation at 54 degrees Celsius. It should be very similar, very near to 90 degrees Celsius actually. I will start with the heating in this oven and I will measure the temperatures with this cooking thermometer. And this is a time-lapse without digitally zoomed in, and here you can see the values. And as I predicted, they start with deformations on very similar temperatures, so let's turn it off. And even for the touch, very similar materials, equally soft. They are still warmed up, but I could take them out with my hand now. And very similar for the feeling. So definitely I think that's some kind of mistake in that property table by the eSUN for the ASA. The creep test will show us the deformations along the time during the constant load. So this is the C-test specimen from the ABS, and this one is from the ASA. 1.25 kilogram load. And now I will lock the position with this holder and measure the distance between these two surfaces. ASA 15.63, ABS Plus 16.18. And I will repeat this every day, and on the last day I will put it inside the enclosure on 45-50 degrees Celsius. ASA 16.21, ABS Plus 16.64. So this is the state after one day. I already measured it, so these are the dimensions on the day 2. And this is day 3, basically almost no changes on ASA test object, but very minimal on ABS Plus. Day 4, and these are the numbers. For ABS, basically I got even a little bit smaller value, but very minimal, so this must be inaccuracy in measuring, but basically the creeping completely stops in both cases. And this is day 5, basically no significant differences, so the creeping was stopped completely. And now it goes to the heated enclosure and then the final conclusions. I heated up the temperature with this A blower to 50 degrees Celsius, and now I have filament dries which will keep on this temperature, and currently it is 50 degrees Celsius inside, and I will measure the creeping after 1 hour. And it's time to finish the experiment. The temperature went up to 51 degrees Celsius. ASA 16.52. Almost no changes. ABS Plus 1769. And this is almost half millimeter creep on 51 degrees Celsius 1 hour. I always like to record the removing of the load. And here they are side by side after removed load. This is the second type of the creep test where I'm simulating the material creeping under the screw tension. The ways only hold the nuts. So I tight it, and tomorrow I will check if I can tight it even more, and I will measure with this angle meter. And same with ABS. And now let's see, after one day, if I use the same torque, can I apply more rotation on these bolts. $18 and $20, I will calculate the average later. And now ASA. Very similar results, 14 and 21. Day 2, starting with ABS. Approximately 8 and 10 degrees. And this is ASA. Approximately 7 and 9 degrees. Day 3, ABS. No changes. ASA, no changes. Day 4, ABS. No moving. ASA, no movement. Day 5, this is the ABS. No difference. ASA, maybe 1 degree. And after 1 hour heating inside the enclosure, I repeated this torque test. Degrees. And it's time to analyze the results on one place. This Excel table you can download from my website, the link is down in the description. These are results for the creep test, and with the red background I mark where I think that is a significant difference, but all other specifications were very similar for these two materials. But maybe let's see the graph, it's better if it's more visible. So the creeping of that C test specimen, after 1 day basically it stopped with the creeping, very minimally. I noticed some creeping after this 51 degrees Celsius inside the enclosure with ABS plus. On ASA no significant difference. About that screw creep test, after second day basically no creeping was noticeable. Even this is very minimal, so I would say there is no big difference between these two materials. And here the scale is equal, so from these three I think this is the most important to mention, the layer adhesion. With ASA it was 2.5 times bigger than ABS plus, and for most applications this is extremely important for me. For the tensile test and shear stress, it's very similar, so I wouldn't say there is any big difference. The bending test very similar, and the torque test also, and here again we have a bigger difference, but now ABS plus is much better in that impact test. And actually this is just guessing because the test specimen didn't broke. Heat deflection temperature, I'm very happy that information in the property tables for ASA is error, and basically it was even better than the ABS plus, because this is very important for these materials. And the last was the hardness test, which is basically the same for both materials. And don't forget, on my website you can download the specification table from that previous video where I compared PC, PA and ABS plus. It's on the bottom of this page. And the final thoughts, I would like to thanks to eSUN for sending me these filaments, but also I would like to thanks to my Patreon supporters or buy me a coffee donations, because otherwise I will test this with the white filament, but thanks to those comments I decided to buy this one in black color and to compare this one. The results are similar basically like with the white color, and actually now I noticed that the white color arrived on this transparent spool like ASA. This which I bought here in Hungary arrived on this black spool. But from a mechanical aspect they are very similar. So basically the ASA, it's expensive material, but it has two big advantages. One is it is UV resistant, which I didn't test, but I know that that's the specification of the ASA. And the other is, which is very important for me, the layer adhesion. It's more than 2 times bigger compared to the ABS plus. In both cases I got the same, a little bit weaker layer adhesion using the same G-code. The ABS Plus has two advantages. One is the price, and the second is that impact test. So if you are using that application where that's important, in that case the ABS Plus may be the better choice. But don't forget that's only perpendicular to the layers, because here we have that weaker layer adhesion. If that would be affected in that impact, in that case it would be again weaker compared to the ASA. I hope I could cover most important tasks. If I skipped something, please write me down in a comment. Thank you for watching and happy printing!